Now we are going to our first talk by Professor Pardalos from University of Florida and also High School of Economics in Nizhny Novgorod. Professor Pardalos is well-known internationally recognized scientist in computer science, and he is also our old friend. We cooperate since 2011, starting from a mega grant project, and actually we continue with the laboratory of algorithms technologies for network analysis. Panos?
Hello.
Yes. Please.
Thank you, Valerie, and thanks everybody, and welcome to the conference. I'm sorry that I won't be there face-to-face, but today technology is very useful. Let me share my talk here 1 second. The title of the conference is, interesting, and it has to do about a lot of data and intensive computing. And I think nobody will dispute that today networks bring a lot of data we have to analyze. And everybody lives with networks, okay? Forget about social networks that we're all connected with Facebook, with LinkedIn, with histograms. But as you are going to see, many other types of networks. So I thought it was a good idea to give a historical perspective from my own point of view and to discuss some of the advances in networks, okay? I will start from the ancient Greeks, since many of the fundamentals of sciences that were developed thousands of years ago. One of the oldest shortest words, yes and no, are those which require the most thought. And definitely in binary logic, we have bits 0 and 1. And these are very fundamental. The simplest, the most deepest sometimes. And I will mention that Pythagoras maybe was one of the first people to consider the concept of networks because he associated numbers with a scale in music. So numbers and music was one of the first networks, but of course Pythagoras did many other things. Was the first to identify the word cosmos, and also many other words that we use today, like symmetry, melody, very beautiful words that are used in many of the Western languages. But after Pythagoras, we had several thousands of years without any progress, okay? And only just in the 18th century, I will say that graph theory or networks, they started with a very famous Euler problem, okay? Trying to solve the Königsberg bridge problem. At the time that of course, this was a very simple problem, okay? We have here 7 bridges, and you want to start from one point to go back to another by visiting only once each bridge. And but Euler, to solve this problem, transformed it to a graph, to a network. And then, of course, generalize this to a large network with a known number of vertices. So it was the first time Eulerian paths were developed, okay, and the first time for, I would say, the genesis of the network theory. But later on, we had the industrial revolutions, okay. Electricity came to play a major role, okay, in humanity. And one of the major developments in that time was Kirchhoff, okay. Kirchhoff's initiated the theory of electrical networks and was the first person to define the flow conservation equations, one of the milestones of network flow theory. And we use them today. So essentially, these days, also, it was the first time we started discussing the electrical grids, okay? Huge networks. And today, probably these are the largest man-made networks, okay? Huge networks. If you consider in Europe, in the West, in the East, the electrical grids are some of the largest networks. And of course, always they must satisfy the Kirchhoff's flow conservation equations, okay? So later on, we had starting the telecommunication networks, okay? Graham Bell developed the telephone in the 19th century. And this gave a lot of stimulus to many types of researches. And along Bell was also Nikola Tesla, that we have to give him a lot of credit because probably was the first person to conceive the smartphone, okay, in 1926. And Bell was a very controversial person, but many of the smart discoveries, who are done by Tesla. Tesla did many things, was a visionary. And so in the 19th century, we had not only electrical networks, but also telecommunication networks. They started, Of course, this was lines of networks, physical networks. And the field started evolving drastically in the 19th century. And amazingly, the first book was written only in 1936, not many years ago, by Kenning, okay? And that was the first book in graph theory, very interesting book, even for today's standards. And later on, we had the World War II, and unfortunately, wars many times generate a lot of good ideas as a consequences because you have to solve many problems. And one of the major problems they had to solve was supply chain network problems. Okay, many algorithms and techniques were developed to solve logistics problems for the military. And after the war, these technologies applied successfully to many other fields. So in that time, we start developing the first algorithms for supply chain networks, okay? And we see that these problems remain to be challenging today, especially after the COVID. We see disruptions of supply chain networks and how do we make them robust and how do you make them efficient? Now we have a lot of data and we try to analyze, but supply chain networks remain very challenging problems today. During the same period, we had to solve fundamental optimization problems, okay? Optimization started generating algorithms and models. And the earliest linear programming model was developed by Leonid Kadorovich in 1939 to plan expenditures to reduce the costs of the army, again, for the military issues, okay? And later on in the West, also Kopman's formulated linear programming models to select shipping routes to send commodities from America to specific destinations in England. So people who are fighting against the Nazis and they collaborating these days, okay? So both these people, Kadorovich and Kopmans, they won the Nobel Prize in economics, okay? Of course, Kadorovich was, Kopmans was more famous also for introducing the famous quadratic assignment problem, which still remains open today because there are no algorithms that routinely solve quadratic assignment problems of dimension more than 15, okay? And this problem is you have a set of locations, you know the distance between the locations, say n locations, and you have n facilities, you know the flow of materials between the facilities, and you want to assign the facilities to locations to minimize an interaction of cost and distance, okay? And there are problems generated in the 1960s of dimension 60, 90. Nobody can solve them today. Still remain open. And of course, we have powerful heuristics. And this problem generalizes also to multi-dimensional assignment problems. And these remain very challenging because the same problems in statistics are called data association problems. in computer science, the mapping problems and so on, different names. But since the time of Kaufman's, still remain unsolved and very challenging, okay? And anyway, so this was done some time ago. And after the war, also, both in the West, in the East, in Europe, they start building a lot of highways, okay? For example, the United States has a very amazing highway system. It was built after the war, okay? And so because of these highway systems, they have to solve many transportation problems, okay? So now we have transportation networks, okay? And in many classical books, they consider Hitchcock's algorithm one of the best algorithm for transportation problems. Not unfortunately, but later on they found out, that was a Russian guy. His name was Tolstoy, not Tolstoy, the famous author, okay, literature guy, but he had a much more efficient algorithms. And if you see in this, in this page here, I have a map. And that was the map of the Soviet Union, and the West knew the transportation network. That was classified some time ago. And they wanted to disrupt the movement of things from the east part of the west part of the Soviet Union to the east part. And Tolstoy had very fundamental algorithms for this. But anyway, this today is not classified. And it was a paper written by Shriver some years ago in math programming that gives credit now to Tolstoy. That has a much better, more efficient algorithm than Hitchcock. So transportation networks, they started only after the Second World War. Now, of course, we move things by sea, so we have marine things, okay? Even unmanned ships, okay? We move things by the airplanes, and airlines, they have their own departments. They have to deal with these transportation problems. And there are many, many challenging problems everywhere, by land, by sea, and by air. And of course, I mentioned linear programming because in early days, George Danzig developed a very efficient method, the simplex method to solve linear programming problems. And this method was adapted to solve network simplex algorithms, where the constraints come from a network, okay? And we have very, very efficient algorithms for this type of problems. Although we know still that the simplex algorithm is, worst case complexity can be exponential. Some of the network simplex algorithms are very efficient, okay? And after that time, many authors proposed efficient algorithms for solving network problems. One of the basic network problems is the minimum spanning tree problem. A spanning tree is nothing else, is a tree that touches all the vertices of the network. And so fundamental algorithms for this problem are very important. And one of the first algorithms was by Kruskal and Prim, a greedy type of algorithm, okay, that solve efficiently the minimum spanning tree problem. And also minimum spanning trees are the basic physical solutions in the networks, okay, when you consider them. So extremely important. And later on in 1956, the Dutch mathematician Dijkstra found one of the most efficient algorithms for the shortest path problem. You have a big network, you go from one place to another in the shortest path. He gave again a greedy algorithm that was proved to be optimal, and still today remains one of the most used, the most efficient algorithms. I had a chance to meet Dijkstra in 1985 in Austin, Texas, because he got the Turing Award for his developments. Okay? He was an amazingly smart guy. But today, the networks are so massive, okay, you try to find just approximate shortest paths. And many times you also want to find safe paths, because what depends what do you move along the paths, or nice paths, depends on many applications. So the concept of the path has been extended, and the size of the networks where you want to solve the shortest path problem are huge, massive. So, but these were developments in the 1950s. And later, if you remember, the data structures were introduced in computer sciences. Robert Townsend from Bellam's wrote the first book on data structures. And using data structures, many of the designed algorithms became very efficient in complexity and also in practice, okay? And one of the first books that incorporates data structures and complexity, computational complexity, is the book by Ford and Fulkerson. I recommend this book. This is a classic book to all the young people that they study networks. So that's one of the the first book that used data structures to study networks. Very amazing. And of course, in recent years, because of many evolution of computers, changed the field. We now aim to analyze large scale networks, okay? I would say massive networks, okay? And we developed, of course, since the 80s, we have parallel computing, okay? Parallel algorithms, some green computing. Now, people, they solve problems in the cloud, sky computing. NVIDIA developed the GPU and make things much faster because some of the problems are so big, okay? Only with GPUs can you solve them. And of course, we have also quantum computing, although we have a lot of simulators, still we don't have any real quantum computer. Okay? We have models of quantum computers, and hopefully in the future, we're going to be able to solve really too many challenging problems in networks. Okay? So network analysis has definitely developed a lot the last few years, okay, in connection with many other disciplines. And because also there are so many applications of the networks, of course, in operational research, I mentioned supply chain and other things. In computer science, okay, in transportation, found many applications in biomedicine, okay. In fact, I have a book some years ago, Clustering Challenges in Biomedical Networks, Energy, studied from the grid and so on. And the last few decades, social networks, okay. A lot of companies have been developed to just analyze social networks. Only Facebook or Meta these days, the networks are huge, billions of vertices and billions of connections. Computational neuroscience networks have been very useful to analyze many problems in the brain. And it's amazing today, if you go to any neuroscience conference, they have special sessions on networks in neuroscience to analyze many parts of the brain. So a lot of developments and a lot of applications, okay? I'm not going to go through all of this. I will tell some of my own approaches to these areas, okay? For example, we published some years ago the handbook of combinatorial optimization. The second edition came out, okay? 7 volumes, okay, with Ding Dewey and Donald Graham. And now we are working on the 3rd edition because it got a lot of what has been accepted a lot by the community. And why combinatorial optimization is related to networks? Because there is a fundamental result that says every combinatorial optimization problem can be reduced to an equivalent shortest path problem. So shortest paths are very fundamental, okay? Of course, we know that many of the combinatorial problems are NP-complete. So when we do this reduction, the network becomes exponentially large. But nevertheless, this approach has been very useful, especially when you design approximate algorithms for many of these difficult problems. So shortest path is a very fundamental problem. And so recently we published the book, Introduction to Combinatorial Optimization. And in this book, we discuss many of the fundamental problems, maximum flow problems in networks, minimum cost problems and the shortest path problem, because all of us, we know that these three are equivalent, okay? If you solve one efficiently, then you solve the other efficiently. And this, by the way, this book has been translated in some languages. It can be used as a textbook, but it's a modern book that covers many of the modern applications. And many other books has been written, editing or handbook of optimization in complex networks. The first one has to do with the theory. The second is dedicated to communication and social networks, okay? And covers a lot of theory and a lot of applications too. Mathematics of aspects of network routing problems. This was done with a past PhD student of mine. He worked in Amazon. Amazon, as you know, has to solve many, many transportation problems. Still, that's what they work, okay? Transportation problems. And I should say that a couple of years ago, we organized the DIMAX implementation challenge on routing problems, okay? And so if someone has an interest, we can visit the DIMAX webpage to see the winners of this challenge, okay? Because still routing problems remain very challenging, okay? And of course, networks, they move information, and we organize many conferences on cooperative systems or dynamics of information systems, and here are some of the books they address these questions and many proposed algorithms. But again, I should say, after the late 1950s, we had major developments in theory of networks. For example, Erdos and Rinoan developed the concept of random graphs, okay? And later on was the concept of 6 degrees of freedom by currently. And the study that was conducted by Watts and Strongett presented the transition of a network from one extreme case, regular networks, to another one, random networks. Probably you know that book because it also discusses the 6 degrees of separation, and the shortest path in a social network between me and any other person. One knows one is the diameter is at most on the average 6. And the most interesting observation was the development of the type of network, small word networks, okay? Very important as an application, and I know especially in these kind of big applications in neuroscience. So the results of the study on 3 different types of networks, from regular to random to small word, increase the usage of network theory in solving real world problems. And one of the problems I use of the network theory is in analyzing complex systems, because many complex systems are modeled as networks. Okay. Of course, networks appear a lot in nature. Networks provide information on which system components interact with each other, putting aside the mechanism of these interactions. And the dynamics of the system is tightly connected to the structure of the underlying network. Studying the topological properties of the network system network can provide an insight about the system's high-level structure and its function. And this has been applied to many, many important problems, okay? I will tell you a few things about my work with my group and also with Latin, some of these works. We did over the years we did a lot of work on telecommunication networks. In fact, we were the first to analyze the AT&T call graph. In this graph, vertices are the phone numbers, and the connections are if one calls someone, so there is an edge. And about 20 years ago, we were asked to analyze this huge graph again. For example, we had to solve click problems in graphs with over 70 million vertices and several millions of connections. And the first observation was this graph was not a random graph, but empirically we saw that this graph was a power law distribution graph. Very important characteristic, because later on, they found that many networks in nature, they are power law networks, okay? And what the amazing thing in this huge network, the largest click we found was around the size of 30, and was a lot of media attention. Why we have such small communities and so on and so on. Many papers came out in about this in The Economist, in American Scientist, and so on and so on. But anyway, this work gave motivation to many other works. Later on, we started to start working on financial networks, okay? In fact, we did a lot of work with many people in Nizhny for the market graph. Here, the vertices are nothing else but financial instruments and connections. This we start with a complete graph, okay, and the weights are based on correlations of price fluctuations over a period of years, and then we filter this graph, and again we filter based on certain threshold. Okay, we find out that these graphs again are power law distribution graphs. In the beginning, when we considered this problem, we wanted to study what does it mean, how to quantify globalization, okay? And we observed that the clicks in these graphs become bigger and bigger as the time goes on, and the independent sets become smaller and smaller. But in practice, independent sets correspond to diversified portfolios. So it explains the fact why it's difficult today to construct large diversified portfolios, because later on, many other studies came and they proved that, for example, about 1,500 stocks dominate most of the wealth in the planet. It's because many of these big companies, they buy smaller companies, and so there is no independence, okay? And in fact, in the banking system, it's even worse because less than 50 banks dominate 80% of the wealth in the planet. Of course, things they change, geopolitics they change, things they change, okay? But again, there's a lot of this work of ours. We published also the book of telecommunication networks, generated a lot of work by many other people and had a lot of feedback in this field. And later on, we worked on brain networks. In particular, we focused on two types of networks: epileptic and Parkinson network. The first one based on the electrical activity of the brain. And here we have a lot of freedom on how to collect these networks. But in the epileptic network, we found out that before, for example, an epileptic seizure and after an epileptic seizure, we see different patterns of connectivity of this network. And this indicates it can be used as complementary help to predict seizures and also to control. Okay, we had a lot of work in this area, and even a startup company, Optima Neuroscience, that was later on sold. And for the Parkinson brain, based on the magnetic activity of the brain and fMRI, again we define networks. Okay, again the vertices here of the network were parts of the brain. Okay, and then analyzing this time series with the wavelets, the weights of the wavelets were parts, the weights of this Parkinson graph. But we used some elementary, for example, social network measures like total efficiency, who aimed to separate the Parkinson brain from the default brain. So it was very important, I think, development. And of course, this applies to many biological networks, okay? And the body has a lot of networks. It has the vessel network, has the respiratory network, many. And all of them are connected, in fact. And we did a lot of work also on social networks. Of course, today the field of social networks has been completely expanded, but we focused on sports networks, okay? In fact, we have several books. One book also with Latina, social networks in sports, because we studied the movement of players from one club to another, the relation between athletes, and so on. And some years ago, just before the pandemic, I organized the Harvard School of Economics in a conference on social networks. Okay, it was amazing because together with the sports networks in Moscow. I think that's the only, the sports university in Moscow. That's the only university in Russia that is dedicated to sports, okay? And I collaborated also with the sports university in Seoul, Korea, because also that's amazing. 2 universities that specialize only on sports, okay? And the networks play an important role there. Like, for example, in authors networks, we have the editors number. Many of you, they know that, who, if you write a paper with authors, your editor's number is 1. If you write with a co-author of editors, your number is 2, and so on. This is a very important social network. In sports network, we define also, for example, basketball, Jordan number. Jordan was a very famous basketball player, and, you see the same type of ideas. They can go to many, many things. And for transportation networks, we also developed many algorithms, in particular for evacuation networks, because in the south of the United States, we have a lot of hurricanes. And probably you saw the news the last month. We had in Florida 2 hurricanes, one after the other. It was amazing. A lot of damage was caused. And a fundamental problem here is how to evacuate people from one place to another. And sometimes part of the network is destroyed. And even sometimes small tricks like reversing the direction of one highway can save a lot of lives. But we have several papers on this problem. But still, this remains a very difficult problem because it's a stochastic network problem, okay? And also we worked on smart grid for this problem. One fundamental problem here is how to detect and control blackouts, because blackouts today can be induced by many ways, okay? By people, by mistakes, by cosmic phenomena. For example, the sun's activities can cause disruption in the grid. It happened some years ago. The Quebec network, because of sun's activity, went down, and this caused a blackout in New York. If you cause a blackout in a big city, this definitely creates major problems. And we know recently Cuba had a blackout for many days because of these hurricanes. So blackouts are difficult problems, and still, although we have a lot of data, still we cannot properly analyze it, okay? It's not easy to analyze. And many algorithms have been proposed. And on smart cities, today smart cities are very important because many networks are joined together, telecommunication, water networks, cybersecurity networks, and so on and so on. And of course, this gave rise to massive networks because all of them are very big, okay? Huge. And now we come to the most challenging of all. In the school, in the university, we teach the students one network, how to analyze a specific network, okay? But now we have networks of networks, okay? And the first of them, there is the Internet of Things, a worldwide network of interconnected objects that are uniquely addressed via standard communication protocols. In the internet, we have many things together. We have pages, they have text, they have video, they have voice, they have everything, okay? Very challenging problems and there are many developments in the theory of networks, okay? But many of them are not known in books or because many can be developed by big companies, like Microsoft, Google, Amazon, and they don't publish these results, okay? And of course, we have now cooperative networks. Since the field of unmanned vehicles has been developed a lot, cars, they drive in the highways without a driver, but they must cooperate with other cars. They must communicate and cooperate. And cooperative networks have been developed a lot. I have a few books on cooperative networks if someone is interested. And the simplest case is the multicast networks. Different networks of the same type, they are connected together. A good example of multicast networks are the airline networks, alliances, okay? Many airlines, many times you fly and you see this is a Delta flight, Air France flight, and KLM together. So they conjoin things. So these are multicast networks and of course interdependent networks. And many things. And lately we have sustainable interdependent networks. Sustainability comes everywhere, okay, because it's a fundamental aspect, okay, with sustainability. And here we published several books. I will mention some developments, because if you have a network, there are many fundamental issues, okay? What are the most important elements of this network? For example, you want to protect your network or you want to destroy a network. For example, in a grid, you want to protect the fundamental parts of the network, so you don't cause you have a blackout in a place, this blackout does not propagate everywhere, okay? So critical elements are very important, can be critical vertices, can be critical edges, can be critical paths, and can be critical clicks, and all together, okay? Mathematically, you can say, if you give me a number k, what is the smaller number of vertices less than k that I can delete, and the network preserves connectivity. One issue is connectivity, the most important, the simplest issue, okay? To preserve connectivity. So if I destroy certain parts of the network, if I destroy or protect, I preserve connectivity or destroy connectivity. In fact, the first project we had to solve here is how to you want to disconnect a telecommunication network, a telecommunication network. And then you have to identify the elements to destroy, so people in that network, they cannot communicate with each other. And this is very important many times in terrorist networks and so on and so on. And also robustness of this network, how to keep robust the network. We know a network is robust if part of this is destroyed and still functions. But how do you quantify this? And recently we developed a new measure of robustness based on a different representation of a network. We know usually a network is represented by its adjacency metrics, okay, a 0-1 matrix. 1 if there's a connection between 2 points, and 0 otherwise. But we replace now this with the probability vectors, okay? For example, Aij is not 1 and 0, but Aij is the portion of vertices in distance j from I. So it's in the adjacency matrix, each row now becomes a probability vector. And this gives us a chance to define new measures of robustness. This is the paper here, the last paper here in Nature Communications, because if you destroy a network, it changes in size. So you have to measure quantify distances, dissimilarities between networks of different size, and therefore we define a new measure of robustness. Okay. Now, amazingly, all these critical element problems are very difficult to solve. In this first paper, we discussed complexity and approximation algorithms for these problems. I won't go to the discussion here. But even for special graphs, special networks, these problems are very difficult to solve, are NP-complete. And of course, almost all these problems have very compact integer programming formulations. But unfortunately, you cannot solve them exactly for large-scale problems, okay? Because sometimes these networks are very big. So the new challenge now we have today, people talk about large networks and massive complex networks, okay? And we know that, for example, the social networks, telecommunication networks, the smart grid, financial are huge, very huge, okay? This, after we did the work on the cold graph, these days we had to, the data did not fit in the memory of the machine. So you had to use semi-external memory algorithms to solve this problem, okay? Semi-external. Today, because the data is so big, massive data sets doesn't fit in the memory of the machine. People are using external memory algorithms, much more sophisticated algorithms. We published the first book, okay? The first book on massive data sets about 10 years ago, okay? 10 to 11 years ago. The two people, James and Bello, who are in Belams, Mauricio resented. Now Mauricio went to Amazon, but now he retired. But anyway, this book is also a massive book. It's a big book, okay, that discusses many. This is the book, okay, discusses many of the challenges in the when you have to deal with massive data sets, okay. So external memory algorithms, how to represent the problems in data, different data structures, and so on and so on. I think it's an important. As I know, since then, only one book has been published on massive data sets. So because there are a lot of results, many of these big companies, they use these results, but they don't publish it. And there are some other books I mentioned here is, for example, these two papers here discuss many new challenges. And now we come to interdependent and multiplex networks, okay? Many complex systems are represented not by a single network, but by sets of interdependent networks. In the simplest case, interdependent networks are equivalent to the so-called multiplex networks I mentioned you before, containing vertices of one type, but several kinds of edges. And connectivity properties of these networks and their robustness are different from ordinary networks. Many times the theory we develop just for a single network, they don't transfer to networks of networks. So you have to develop different types of theories. Very challenging new problems, okay? I'll give you an example here. This comes from smart cities. You see, in a smart city, we have many networks that they must interconnect. And these are diverse networks, different, okay? Telecommunication networks, water network, the electric power, the energy network, transportation networks, all these, they communicate together for an efficient smart city. And these are diverse, not the same, okay? Diverse networks, okay? So and also cybersecurity networks now, they go to all of them. In the concept of a smart city, for the future is very important and very complicated, okay? Financials. The international financial system has a lot of interconnections. And these are not the same, you know. For example, the blue note here is on the North America, for example, Bank of America, Goldman Sachs, and so on and so on. Some are in Europe, some are in Asia, and you see all of them are interconnected. And any disturbance on these financial networks causes a lot of problems. Imagine now what happened with, with the East and the West, with the conflicts. The system has been interrupted. And also what happens in one country has a lot of effects in the other. Sometimes you have a crisis in a small country like Greece or Kuwait. It affects the stock market in New York or in London, okay? So this interconnectivity causes a lot of volatility issues also. But it's interconnected. You cannot just isolate. The system is interconnected. Yes. How many more minutes I have? It's time? Okay, go finish here. Anyway, we identified also the diversity. What is diversity? Because as I showed you before, we have, again, based on the new representation of graphs, but I won't go to the applications here. Someone can see the paper here, and we had many interesting results in this analysis here. But I want to say a few things about this in sustainable interdependent networks. Many fields, they go together, okay? And to solve many of these problems in social sciences, in engineering, in operational research, and so on and so on. We started an effort to publish several books here for many people. And already we published 2 books. The first one is Sustainable Interdependent Networks, from theory to in application. The second one focuses on the smart powered grids, okay, and transportation networks. And now we're in the process of having more books in this area. Sustainability also is a very difficult concept to define because it has many dimensions. Social, economic, and so on and so on. But we hope that all the networks we construct are sustainable for future generations. So I think this is my last, I think I wanted to mention that we recently, actually the last year, we published a special collection of papers on networks with Valerie and Mario Grassino in Italy. Now we have a new collection of papers in Operational Research Forum on networks and decision making. If someone has an interest, please submit a paper. The deadline is December 1, 2024. Already we have several papers in this submitted so far. So I think I'll stop here, and always I end my talk with a very nice quote of Heraclitus: "The hidden harmony is better than the obvious." Okay, nature hides many things, and we have to discover them. So I hope I covered my time. Okay, and I entertain now any questions you have from the audience. Please.
Thank you.
Any questions?
Questions? We have time for small questions.
Too many questions.
For extremely interesting introduction of the network and the network analysis, I have a question regarding how to implement ideas of network analysis in the school curriculum. Why? Because it's extremely evolving story, and even people without deep technology skills, they should understand how to apply. Do you have any thoughts how it can be implemented so school children can know the ideas of network analysis? Thank you.
Valerie, can you repeat the question, because it's not easy to hear too well from.
The question is, what do you think about network implementation in educational process?
Of course, already young people, they use a lot of networks. Of course, they use them as black box. They use Facebook, Instagram. They use LinkedIn, and but networks can be used in education, because some of the examples that I mentioned before, in a small scale, can be taught in schools, high schools. Transportation networks, for example. We use every day, and also the electrical networks, again, because they learn physics, and all these ideas, behind all these networks, the fundamental tools are the same. You use the same tools, okay? Mathematics, and the same tools can be used in, and everybody can understand the shortest path and explain why it's so important, okay? And the minimum in the spanning trees. These are concepts that are not difficult. They start teaching today in high schools, and students can find them very interesting. If I answer the question, and definitely these things can be introduced to low-level education, not only to university.
Okay, because we are short in time.
Okay, thank you so much for your attention. It's too late for me. My brain is not very clear. It's only now almost 4 o'clock in the morning here.
Okay. Now we thank you, Panos.
Thank you very much. Let me stop sharing.